You're not here because you want to panic. You're here because on a Tuesday morning in March 2024, a simulation finished running at the European Space Agency's Dynamics Lab in Darmstadt, and 3 people in that room stopped talking mid-sentence. Not because of an impact prediction, not because something was coming for Earth, but because the numbers on the screen showed an interstellar object doing something that random comets simply don't do. 3I Atlas, the third confirmed visitor from beyond our solar system, was steering itself with surgical precision toward the one region of space where Jupiter's gravity could catch it, slow it, and keep it. The odds of that happening by accident? 1 in 25,000. You clicked on this video because that number bothers you the same way it bothers the scientists who calculated it, and you want to know what it means. So let me show you. The night it changed. The discovery of 3I Atlas didn't happen with fanfare. It happened the way most astronomical breakthroughs do, quietly, in the middle of the night, by someone who wasn't expecting it. January 27, 2024. The Atlas Survey Telescope in Hawaii, the same system that watches for near-Earth asteroids, flagged a faint streak moving through Orion. Just another dot, nothing special. But when the follow-up images came in, something was off. The motion was wrong. Too fast, too steep. It wasn't orbiting the sun in the gentle ellipse that native solar system objects follow. It was cutting through space at an angle that screamed outsider. Within 48 hours, observatories across 3 continents confirmed it. The object's trajectory was hyperbolic. It came from interstellar space, and unlike most visitors, it wasn't just passing through on a one-way trip. It was slowing down. Not dramatically, not like hitting brakes, just enough. By February, orbital dynamicists had refined the path, and that's when the unease started creeping in. Because 3I Atlas wasn't wandering aimlessly through the solar system. It was threading a needle so fine that even the most experienced modelers had to double-check their work. It was aimed at Jupiter's Hill sphere. What is the Hill sphere? You've probably never heard the term Hill sphere unless you're deep into orbital mechanics, but it's one of the most important invisible boundaries in the solar system. Around every massive object, planet, moon, star, there's a zone where its gravity dominates. Inside that zone, smaller objects can be captured, held, stored. Outside it, the sun's gravity wins, and things drift away. Jupiter's Hill sphere extends nearly 50 million miles outward from the planet. It's a vast, invisible shell of gravitational influence. And here's why it matters. If you wanted to deliver something to the Jovian system, Europa, Ganymede, Callisto, you wouldn't aim for Jupiter itself. You'd aim for that shell. You'd let Jupiter's gravity do the work. It would slow your object, bend its path, and guide it into a stable orbit without tearing it apart. That's exactly what 3I Atlas is doing. Not crashing, not skimming the clouds, not spiraling out of control. Threading into the one zone where Jupiter can gently catch it. And the precision required to do that is staggering. The 0.04% problem. Let's talk about probability for a moment. When scientists model random interstellar objects entering our solar system, they run thousands of simulations. Comets from deep space come in at all kinds of angles, speeds, trajectories. Most sail through and leave. Some get deflected by planets. A few crash into the sun. But the odds that a random comet would enter at the exact angle 3I Atlas did, swing past Mars and Venus in the way it did, line up to intersect Jupiter's Hill sphere at its measured velocity, those odds come out to about 0.04%. 4 chances in 10,000. You wouldn't bet on those odds. You wouldn't trust them. And neither do the scientists who calculated them. Because here's the thing about probability. When something unlikely happens once, it's chance. When it happens twice, it's a pattern. And when the only explanation that fits requires an object from another star to know where it's going. You start asking questions you never thought you'd have to ask. Dr. Elena Vorontsova, a dynamics specialist at ESA, said it plainly during a closed presentation. This is not the trajectory of something lost. This is the trajectory of something aimed. She didn't use the word artificial. She didn't have to. Before we even understood the trajectory, something else was wrong. Comets brighten and dim in predictable ways. As they approach the sun, they heat up. Ice turns to gas. Dust gets blown into space. The coma, the fuzzy cloud around the core, grows brighter, peaks, then fades as the comet moves away. It's a rhythm astronomers have studied for centuries. Predictable, reliable, boring, even. 3I-ATELAS doesn't follow that rhythm. When Hubble turned its attention to Atlas in March 2024, the light curve looked like noise. Brightness spiking at random intervals, dimming without corresponding changes in distance or solar heating. Some regions of the object seemed to flare independently, as if different sections were activating out of sync. There was no clean rotation curve, no simple explanation. It was as if the object had zones, patches of surface that brightened on their own schedule, regardless of what the rest of the comet was doing. Dr. Yuki Tanaka, an optical astronomer at Subaru Observatory, described it in an email that later circulated among colleagues. It's like watching Christmas lights that forgot they're supposed to blink together. Comets don't do that, but something with structure might. Then, JWST took its turn. The James Webb Space Telescope, parked 1 million miles from Earth, has the most sensitive infrared eyes ever built. It can read the chemical signature of an object's coma, like a barcode. When JWST analyzed 3I-ATELAS, it found something nobody expected. The object's coma was dominated by carbon dioxide, not water. CO2. Most comets are wet. Water ice makes up the bulk of their mass, with CO2 playing a minor role. But Atlas flipped that ratio. It was carrying one of the highest CO2 to water ratios ever measured. That tells you something about where it came from. CO2 ice stays frozen at much lower temperatures than water. For a comet to have this chemistry, it would need to have formed in a region of space colder and darker than anywhere in our solar system's cometary reservoirs. A place between the stars. A place where water sublimates away over billions of years, but CO2 stays locked in place, like a time capsule. But here's what made scientists uncomfortable. CO2 ice also makes an excellent insulator. It shields whatever's beneath it from radiation, heat, and time. If you wanted to preserve something delicate, organic molecules, biological precursors, or something more structured, wrapping it in CO2 ice would be one of the smartest choices you could make. Atlas wasn't just strange, it was designed for preservation. High-resolution imaging from the Very Large Telescope in Chile gave us the next piece of the puzzle. The core of 3I-ATELAS is not spherical. It's not neatly rounded like most cometary nuclei. But it's not also fractured or chaotic like a rebel pile. It's irregular but intact. That's significant because comets are fragile. They're loose collections of ice and dust held together by weak gravity. When they get close to the sun, thermal stress cracks them. We've watched comets split apart during perihelion dozens of times. But Atlas passed perihelion in late 2024 without breaking. Models predicted it should have fractured. Thermal simulations showed regions of stress that should have caused structural failure. Yet the object emerged whole, as if it were built to withstand conditions that destroy typical comets. It's like watching a sandcastle survive a wave that should have flattened it. And then there's the coma structure. Normally, a comet's coma is chaotic, a messy cloud of gas and dust spraying in all directions. But polarimetry measurements from Subaru showed something different. The dust around Atlas wasn't random. It had structure, organized jets, plumes that behaved like controlled vents rather than explosive outbursts. One researcher described it off the record as uncomfortably tidy. Comets are messy. This wasn't. But the detail that no one can explain away happened when Atlas passed behind the sun. When a comet moves behind the sun from Earth's perspective, it should quiet down. Less direct sunlight means less heating. Less heating means less outgassing. The coma should shrink. That's basic physics. Atlas did the opposite. Its brightness dropped as expected, but when astronomers reconstructed the size of its coma using indirect measurements, they realized something unsettling. While the light went down, the coma grew. It expanded in the shadow. Dr. Hannah Reeve from ESA's Planetary Science Division put it bluntly in a conference call. Natural bodies don't do this. They don't save energy for when no one's watching. But something that wanted to adjust its trajectory might. Because here's what happens when you release gas asymmetrically. It creates thrust. Tiny, almost imperceptible, but real. Enough to nudge an object's path by fractions of a degree. And fractions of a degree over millions of miles mean everything. When teams compared Atlas's predicted post-perihelion trajectory with its actual path, they found something uncomfortable. The object's velocity curve was stabler than it should have been. Not frozen, not artificial, just too precise, as if something inside it was compensating. By June 2024, enough data had piled up that denying the strangeness became harder than acknowledging it. In a closed meeting at NASA's Jet Propulsion Laboratory, a senior dynamicist named Dr. Marcus Liu pulled up a summary slide. It listed every anomaly side by side. At the bottom of the slide, in small text, was a single sentence. If it's just a comet, it's pretending not to be one. Someone in the room laughed, but it was the kind of laugh that doesn't relieve tension. It makes it worse. Because once you put all the clues together, you're left with two possibilities. One, 3I ATLS is the strangest, most statistically improbable natural object we've ever observed. Or two, it's something else. And the scientists in that room didn't want to say which one scared them more. Why this matters to you? You might be wondering why you should care about an ice ball 300 million miles away. Fair question. Because this isn't about drama. It's not about alien invasion or conspiracy theories or Hollywood endings. This is about watching the scientific method do what it's supposed to do. Take unexplained data and follow it wherever it leads, even when that place is uncomfortable. You're not being sold a fantasy. You're being shown where the equations stop working. And for someone in their 40s, someone who's lived long enough to see hype come and go, someone who respects honesty over sensationalism, that's exactly the kind of story worth your time. The world's best scientists are looking at 3I/Atlas and quietly admitting they don't have a clean explanation. That admission is rarer and more valuable than certainty. So when you hear the phrase, "it's terrifying," understand what that means. Not scary, not dangerous, just deeply, profoundly strange. And the strangeness is only beginning. Because while we've been analyzing its chemistry and trajectory, we haven't yet asked the most important question. What is it doing when it gets to Jupiter? And why does its path look less like a comet's drift and more like a delivery route? Because once you understand the physics of Jupiter's gravity well, once you see how rare and specific Atlas's approach corridor is, you'll realize why 3 people in Darmstadt stopped talking. You'll see why the word terrifying isn't hyperbole. It's the only honest word left. Let's strip away the mythology for a moment. Forget the Great Red Spot. Forget the swirling storms. Forget the images of a gas giant floating serenely in space like some cosmic marble. What Jupiter really is, at its core, is mass. Stupid, overwhelming, unavoidable mass. More than twice the mass of every other planet in the solar system combined. So much mass that it doesn't just orbit the sun. It and the sun orbit a common center of gravity that sits outside the sun's surface. In the language of physics, Jupiter isn't a planet, it's a gravitational monster. And that mass creates something most people never think about: a well. Not a well you can see, a well carved into the geometry of space-time itself. A pit so deep that anything passing nearby doesn't just feel a tug, it feels inevitability. Most small objects that wander close to Jupiter don't escape. They get whipped into new orbits, torn apart by tidal forces, flung outward at terrifying speeds, or swallowed into the darkness. There is no casual encounter with Jupiter. But surrounding that monster is something even stranger: the Hill sphere. Imagine standing at the edge of a massive bowl, the kind so wide you can't see the other side. If you roll a marble toward it, gravity pulls it down. But if you roll it at just the right speed, at just the right angle, the marble doesn't fall to the bottom. It circles. That's Jupiter's Hill sphere. It's the zone, stretching nearly 50 million miles outward, where Jupiter's gravity beats the sun's in a slow, patient tug of war. Inside that zone, objects can linger, drift, be captured. It's not just theory. We've already seen it happen. Jupiter has 95 known moons. Many of them are small, dark, irregular chunks of rock and ice that wandered too close and got caught. They didn't crash. They didn't escape. They just stayed. Decades, centuries, millennia, parked in a gravitational shell that holds them like pebbles swirling in a bowl. To an orbital dynamicist, the Hill sphere is one of the most important landmarks in the solar system. It's where the rules change, where small nudges mean everything, where an object's future can shift from escape to capture with a velocity change of less than a meter per second. And here's the part that makes scientists uneasy. If you wanted to deliver something to the moons of Jupiter, Europa, Ganymede, Callisto, you wouldn't aim at Jupiter itself. You'd aim at the Hill sphere. You'd let Jupiter slow your object, bend its trajectory, catch it gently without destroying it. And then once you're drifting inside that shell, the moons would be within reach. That's not speculation. That's orbital mechanics 101. And it's exactly what 3I/Atlas is doing. On March 16, 2026, 3I Atlas will pass within 0.358 AU of Jupiter. That's roughly 33 million miles. Close enough to feel Jupiter's gravity, far enough to avoid being ripped apart. But here's what keeps dynamicists awake at night. That distance isn't random. If Atlas were just 0.1% faster, it would overshoot the Hill sphere entirely. It would sail past Jupiter and continue outward into the dark, never to return. If it were just 0.1% slower, it would dive deeper into Jupiter's gravity well. Tidal forces would shred it. Radiation belts would cook it. It wouldn't survive. But Atlas is threading the needle. Its approach corridor is so precise that it minimizes tidal stress, maximizes gravitational capture potential, and positions it perfectly for a stable interaction with the Jovian system. Dr. Samuel Richter at JPL summarized it best. If you gave me a pen and paper and asked me to design the safest way to enter Jupiter's influence from interstellar space, I'd draw this exact trajectory. Not similar, exact. That's not how comets behave. Comets tumble, they wobble, they spiral. They enter gravity wells chaotically because they're at the mercy of forces they can't control. But Atlas? Atlas is surfing. In May 2024, a team at ESA ran a series of simulations. They wanted to understand how many random interstellar objects would naturally end up in Atlas's approach corridor. They modeled 100,000 comets entering the solar system from all directions, at all speeds, with all kinds of trajectories. Then they filtered for objects that would pass within 0.5 AU of Jupiter, enter the Hill sphere at a stable angle, minimize tidal stress, avoid deep magnetosphere penetration. Out of 100,000 random visitors, only 38 met those criteria. That's 0.038%. And here's the kicker. When they looked at how those 38 got there, almost all of them had experienced gravitational assists from other planets first. Venus, Mars, Earth. Something had nudged them into that corridor. But 3I Atlas? It came in clean. No assists, no deflections. Just a straight, efficient path from interstellar space into the one zone where Jupiter could catch it without destroying it. Dr. Elena Vorontsova presented these results in a closed seminar in Darmstadt. At the end of her talk, she put up a slide with a single question. What are the odds that the third interstellar visitor we've ever observed happens to take the rarest, most stable approach to Jupiter we've ever calculated? The room didn't answer, because the answer felt heavier than words. So if Atlas is being delivered somewhere, why Jupiter? Why not Mars? Why not Earth? Why not the asteroid belt? Because Jupiter's moons offer something no other place in the inner solar system can provide: stability. Europa, Ganymede, and Callisto have existed in nearly the same orbits for billions of years. No atmospheric chaos, no plate tectonics, no extinction-level impacts every few million years. Protection. Their oceans are sealed beneath miles of ice, shielded from solar radiation, isolated from cosmic rays, safe from the ultraviolet death that would sterilize anything exposed on a surface. Chemistry. Beneath Europa's ice is a saltwater ocean twice the volume of Earth's. Hydrothermal vents, minerals, organic molecules, everything you'd need for chemistry to happen slowly, patiently, over deep time. Silence. No life already there to compete with, no biosphere fighting for resources, no predators, no oxygen tearing apart fragile molecules. If you were designing a natural laboratory, one where something delicate could be placed and left undisturbed for millions of years, you'd build Europa. But we didn't build Europa. The universe did. And now an object from another star is heading straight for it. Here's how the delivery works. When Atlas enters Jupiter's Hill sphere, it won't crash, it won't orbit, it will slow. Jupiter's gravity will bend its trajectory, sapping kinetic energy without violent deceleration. Think of it like a marble rolling up the inside of a bowl. It doesn't stop instantly. It curves, slows, and eventually settles. Once inside the Hill sphere, small adjustments, tiny releases of gas, subtle shifts in mass would be enough to guide Atlas toward one of the moons. Not quickly, not dramatically, just patiently. A few meters per second here, a slight course correction there. Over weeks, months, even years, Atlas could spiral inward, threading between the orbits of Callisto, Ganymede, and Europa, until it reaches whichever one is the target. And here's the terrifying elegance of it. If you were crossing the galaxy and wanted to deliver something to an icy moon, you wouldn't waste energy fighting gravity. You'd use gravity. Stars as waypoints, giant planets as brakes, hill spheres as harbors. You wouldn't need rockets. You wouldn't need fuel. Just time, patience, and physics. 3I-Atlas has all three. There's one more detail that keeps getting whispered in the back of conference rooms. Europa, Ganymede, and Callisto are locked in an orbital resonance. For every orbit Ganymede makes, Europa makes 2. For every orbit Callisto makes, Ganymede makes 2. It's a gravitational waltz that's been stable for billions of years. And if you wanted to enter that system, you'd need to understand the rhythm. Dr. Luis Marquez, a celestial mechanist at JPL, said it plainly. You don't just stumble into a resonant system like that. You either crash into something or you know the music. Atlas knows the music. Its approach timing, its velocity, its angle, all of it lines up with the current positions of the Galilean moons in a way that maximizes gravitational efficiency. It's arriving when the dance is at the right step. So if all of this is true, if Atlas is some kind of interstellar delivery vehicle, where's the proof? Fair question. The honest answer is, we don't have it. Not yet. We have anomalies, we have statistics, we have trajectories that don't fit natural models, but we don't have a photo of a hatch opening, we don't have a signal saying package delivered. What we have is a pattern. And patterns, especially ones this precise, don't usually appear by accident. Dr. Hannah Reeve, who has spent 20 years studying cometary dynamics, said something in an interview that stuck with a lot of people. I've watched 1,000 comets pass through the solar system. Most behave like rocks thrown by a child, chaotic, random, uncontrolled. Atlas behaves like a stone skipped by someone who's done it 1,000 times before. She didn't say it was artificial. She didn't have to. The implication hung in the air. What if it's wrong? Let's be honest. Maybe all of this is coincidence. Maybe 3I-Atlas is just a deeply strange comet that happened to enter the solar system at a statistically improbable angle with unusual chemistry, strange brightness behavior, and a trajectory that looks designed but isn't. Maybe the 0.04% probability is just bad luck. Maybe the Hill sphere targeting is random. Maybe the orbital timing is coincidence. Maybe. But here's what makes this hard to dismiss. Every time scientists find a new detail, it makes the natural explanation less plausible, not more. The chemistry doesn't fit. The structure doesn't fit. The brightness doesn't fit. The trajectory doesn't fit. At a certain point, coincidence stops being a satisfying answer. And that's where we are now. Stuck between this can't be natural and we can't prove it isn't.
So why is this terrifying? Not because something is coming for Earth. The trajectory is clear. We're not in danger. The terrifying part is simpler. It's realizing that if there is a purpose behind 3I-Atlas, Earth was never part of it. We're watching something pass by on a mission that doesn't need us, doesn't notice us, doesn't care about us. Imagine standing on the side of a highway as a convoy drives past. You're not in danger, you're just irrelevant. That's the feeling scientists describe when they talk about Atlas. Not fear of contact, fear of indifference. If 3I-Atlas is a delivery vehicle, it raises a much bigger question. How many others have there been? We've only been capable of detecting small, dark, fast-moving interstellar objects for about a decade. Before that, we were blind. Oumuamua in 2017, Borisov in 2019, Atlas in 2024. 3 visitors in 7 years. If that rate holds, and if we assume our detection capability is still limited, there could be dozens, maybe hundreds of interstellar objects passing through the solar system every century. Most of them too faint to detect, too far to track, too fast to study. But if even a fraction of them are following trajectories like Atlas, if even a few are aimed at Hill spheres, at icy moons, at stable gravitational harbors, then the galaxy isn't empty, it's busy. And we've only just started noticing. There's one more piece of evidence that makes this theory uncomfortable. In 2005, the Cassini probe discovered something astonishing at Saturn's moon Enceladus. Massive plumes of water vapor erupting from cracks in its icy surface. Those plumes carried organic molecules, salts, heat signatures, everything you'd expect from a subsurface ocean. Scientists called it one of the most important discoveries in planetary science, proof that life-friendly environments exist throughout the outer solar system. But here's what they didn't say out loud. If life-friendly environments are common, and if life is capable of spreading, then icy moons aren't just habitats. They're targets. Places where seeds could be planted, where chemistry could be delivered, where something fragile could be stored, protected, and left to grow over millions of years. Europa and Enceladus aren't unique. They're part of a class of worlds that exist throughout the galaxy. Thousands of them. Maybe millions. And if 3I HELS is heading for one, the question isn't why Jupiter. The question is, how many other deliveries have already happened? Let's think like an engineer for a moment. If you wanted to spread life or technology across the galaxy, you wouldn't send crewed ships. Too slow, too expensive, too fragile. You'd send seeds. Tiny, durable, patient. You'd wrap them in ice to protect them from radiation. You'd aim them at stable, shielded environments. You'd use gravity to slow them down. You'd let time do the rest. A mission like that wouldn't take years. It would take millions of years. But if you're a civilization that thinks in geological timescales, that's not a problem. That's just gardening. And the terrifying part? We might be living in a galaxy that's already been gardened. Europa might already have something sleeping beneath its ice, planted 1 million years ago, waiting for the right conditions. Ganymede might have been seeded during the age of the dinosaurs. And we'd never know. Because we've only just arrived. We're the newcomers. The late guests to a party that's been running for billions of years.
That's the weight scientists are carrying. Not proof, just the uncomfortable realization that the natural explanation is running out of space. And if the natural explanation fails, what's left is a possibility that changes everything. Not about Earth, about the galaxy. Because if 3I Atlas is what it looks like, then life, or something like it, doesn't just happen once and hope for the best. It moves, it travels, it spreads. And we're not the gardeners. We're just one more flower in a field we didn't plant. There's a room at NASA's Jet Propulsion Laboratory where the walls are covered in whiteboards. Equations, trajectories, delta V calculations, spectral data. In August 2024, 12 people sat in that room for 6 hours. Not because they had answers, because they didn't. At the center of the largest whiteboard, someone had written a single question in red marker. If it's artificial, what is it carrying? Nobody erased it, and by the end of that meeting, the room had split into 2 camps. Not hostile camps, just 2 groups of equally intelligent people staring at the same data and reaching different, uncomfortable conclusions. Camp 1 believed 3I Atlas was biological, a seed carrier, a cosmic garden pod delivering prebiotic material to places where chemistry could flourish without interference. Camp 2 believed it was technological, a von Neumann probe, a self-replicating machine capable of using local materials to build copies of itself. Both camps agreed on one thing. If Atlas is carrying something, Earth was never the destination. And that agreement is what makes this conversation terrifying, in the mature, quiet way that changes how you see the universe. Let's start with the biology. Panspermia, The idea that life spreads naturally across space isn't science fiction. It's been debated seriously since the 1970s. We've found amino acids inside meteorites. We've detected organic molecules in interstellar clouds. We know that tardigrades, microscopic animals, can survive the vacuum of space for years. Life, once started, is hard to kill. But starting life, that's the hard part. We don't know how it happened on Earth. We have theories, warm ponds, hydrothermal vents, tidal pools, but no proof. The chemistry is ferociously complex. The conditions have to be perfect, and even then, it might take millions of years. So here's the logic. If life arose somewhere else first, somewhere older, stabler, luckier, and if that life became intelligent, it would eventually realize something profound. The universe is full of places where life could exist, but most of those places are empty. Not because they're hostile, because nothing ever arrived. If you were that intelligence, and if you cared about life spreading, not conquering, just existing, what would you do? You'd send seeds. Not spores blowing randomly on stellar winds, too slow, too chaotic. Most would burn up or drift forever. You'd send targeted seeds, wrapped in protective ice, aimed at stable environments, delivered with precision, and you'd aim them at Europa.
Europa has everything life needs and nothing life fears. Beneath its 15-mile-thick ice shell is an ocean twice the volume of all of Earth's oceans combined. That water is kept liquid by tidal heating. Jupiter's gravity kneading the moon like dough, generating warmth from friction. At the bottom of that ocean, there are almost certainly hydrothermal vents, minerals, chemistry, energy. But here's the key difference between Europa and Earth. Europa is quiet. No atmosphere to burn incoming material, no oxygen to corrode delicate molecules, no competing biosphere, no predators, no viruses, no evolutionary arms race. If you wanted to plant something fragile, prebiotic chemicals, encapsulated microbes, complex organic structures, you wouldn't drop it into Earth's chaotic soup. You'd place it in a sterile, stable environment where it could unfold slowly over millions of years. Europa is that environment. Dr. Maria Klein, an astrobiologist at MIT, said it best. Earth is a rainforest. Europa is a blank canvas. If I were seeding life, I'd pick the canvas every time. And 3I Atlas's chemistry supports this. Its CO2-dominated coma acts as a radiation shield. The water ice beneath would protect organic molecules from UV light. The layered structure suggests compartmentalization. Different materials stored at different depths, released at different temperatures. It's a freezer, a time capsule, a delivery container. And if something inside it survives entry into Europa's ocean, it would have billions of years to grow, adapt, and spread. We wouldn't even know it was there until we drilled through the ice. But not everyone in that JPL conference room was thinking about biology. Some were thinking about machines. Not Hollywood robots, not Terminator-style AI. Something quieter, smaller, infinitely more patient. Von Neumann probes. The concept is simple. A self-replicating machine arrives at a new star system. It gathers local materials, ice, metal, minerals, and builds a copy of itself. Then another. Then another. Each copy travels to a new system and repeats the process. Within a few million years, such probes could spread across the entire galaxy, not through speed, but through exponential replication. And here's the unsettling part. You wouldn't need large machines. You'd need nanoscale assemblers, machines so small they could hide inside a comet, disguised as dust and ice, waiting for the right conditions to activate. Jupiter's moons offer those conditions. Ganymede has a magnetic field strong enough to protect delicate electronics from radiation. Callisto has surface ice rich in water and minerals. Europa has liquid water, heat, and chemistry. If a von Neumann probe were designed to build copies of itself, it would need raw materials, energy, shielding from radiation, and time. The Jovian system provides all of that. Dr. James Corr, a systems engineer at Caltech, ran simulations of how a probe might behave if it were optimizing for long-term replication rather than speed. His conclusion? It would look exactly like 3I Atlas, slow, efficient, aimed at resource-rich environments. No wasted energy, no theatrics. Both hypotheses, biological and technological, hinge on one key observation. 3I Atlas's chemistry looks deliberate. Natural comets are messy. Their composition reflects the random conditions of their formation. Some are water-rich, some are carbon-rich, some are dominated by ammonia. But they don't optimize. Atlas does. Its CO2 shield protects the interior. Its water ice layer insulates fragile materials. Its dust content is high enough to absorb solar radiation, but low enough to avoid catastrophic outgassing. It's layered like a Russian nesting doll, each shell serving a purpose. That kind of structure doesn't happen by accident. Dr. Yuki Tanaka put it plainly. If I wanted to design a comet to survive interstellar travel and deliver a payload intact, I'd designed 3I Atlas. Not something like it. It.
Here's where it gets even stranger. If 3I Atlas is a delivery vehicle, why now? Why arrive in 2024? Why not a million years ago? Why not a million years from now? Unless it's not the first. Think about it. We've only had the ability to detect faint, fast-moving interstellar objects for about a decade. Before that, Oumuamua in 2017, Borisov in 2019, Atlas in 2024, we were blind. Which means there could have been dozens, hundreds, even thousands of interstellar visitors that passed through undetected. Some random, some not. And if even a fraction of them were following precise trajectories toward icy moons, the implications are staggering. Europa might not be waiting for life. It might already have it. Planted a million years ago, dormant, waiting for conditions to change, waiting for the ice to crack, waiting for the ocean to warm. Or maybe it's already awake, already growing, already spreading through Europa's dark ocean while we sit on Earth arguing about whether life exists anywhere else in the universe. This is where the scientists start losing sleep. Because if there's even a chance that something is already in Europa's ocean, then humanity faces an impossible choice. Do we drill? Our Europa Clipper mission is already on its way. In the 2030s, NASA plans to send a lander. Eventually, we want to drill through the ice and explore the ocean beneath. It's one of the most exciting missions in human history. But what if we're not exploring? What if we're contaminating? Dr. Sarah Lynn, a planetary protection officer, put the dilemma plainly. If someone, something, placed biological or technological seeds in Europa a million years ago, and we drill through the ice without realizing it, we could destroy the most important scientific discovery in human history before we even know it's there. Or worse, what if we introduce Earth bacteria into that ocean? Microbes hitchhiking on our landers, carried deep into Europa's water, outcompeting whatever delicate chemistry or biology was already growing there. We'd be committing the greatest act of cosmic vandalism imaginable. But if we don't drill, we'll never know. We'll spend the rest of human history wondering what was down there. It's a trap with no good answer.
But here's the part that really gets under your skin. If 3I Atlas is part of a galactic seeding program, then Earth isn't special. We're not the target. We're not the destination. We're not even on the list. We're just another world orbiting another star. Too loud, too chaotic, too dangerous for anything that needs time and silence to grow. Dr. Neil deGrasse Tyson summarized it in an interview. The scariest thing about Atlas isn't that it might be artificial, it's that if it is, it doesn't care about us. That realization, that cosmic indifference, is the mature version of terrifying. Because we grew up believing that if something visited from the stars, it would notice us, it would land on the White House lawn, it would send a signal, it would change everything. But what if the truth is quieter? What if interstellar visitors pass by all the time, ignoring Earth the way a delivery truck ignores a house that didn't order anything? What if we're cosmically irrelevant? That thought, being irrelevant on a galactic scale, hits differently depending on who you are. For some, it's crushing. The idea that humanity doesn't matter, that our art, science, love, and struggle are just noise in an indifferent universe. But for others, especially people in their 40s who've carried the weight of responsibility for decades, it's liberating. Because if the universe doesn't revolve around us, then we don't have to carry the burden of cosmic significance. We don't have to be important to matter. We don't have to be central to be real. We can just be. Dr. Carla Mendez, a philosopher of science, put it beautifully. Insignificance isn't a curse. It's permission to let go. And there's something deeply calming about that. The universe is vast, ancient, busy, and it doesn't need us to justify our existence, which means the quiet moments, the coffee at dawn, the conversation with a friend, the feeling of rain on your face, those moments don't need cosmic validation. They're enough because you experience them. Before we move on, there's one more parallel worth mentioning: Saturn's moon Enceladus. In 2005, Cassini detected massive plumes of water vapor erupting from cracks in its icy surface. Those plumes contained organic molecules, salts, and heat signatures. Proof of a subsurface ocean, proof of chemistry, proof that life-friendly environments exist throughout the solar system. Scientists celebrated. It was one of the greatest discoveries in planetary science. But here's what no one said out loud at the time. If life-friendly environments are common, and if life is capable of spreading, then moons like Enceladus aren't just habitats, they're targets. If 3I Atlas is heading for Europa, how many other objects have already arrived at Enceladus, at Titan, at Triton? How many icy moons have we overlooked assuming they're sterile when they might already be seeded? We're not the first to look at these worlds, but we might be the first to arrive after someone else already visited.
So why aren't we hearing about this on the news? Why isn't NASA holding press conferences? Why isn't the UN making statements? Because they don't know what to say. Behind closed doors, the conversations are intense. Ethics committees, planetary protection boards, international space agencies coordinating responses. But publicly, silence. Not because of a cover-up, because of uncertainty. If NASA came out tomorrow and said, "We think 3I ATS might be an interstellar seed carrier," the public would panic, or mock them, or demand proof they don't have. So they say nothing. They release dry technical papers. They talk about unusual cometary activity. They emphasize that more study is needed. And in the meantime, the scientists who know the most,
sleep the least. Because they're sitting on a question that could rewrite human history, and they have no idea how to answer it. Remember Oumuamua? The cigar-shaped object that accelerated as it left the inner solar system without visible outgassing? Avi Loeb called it a light sail. Others called it a weird comet. The debate still rages. Remember Borisov? The normal interstellar comet that gave everyone a baseline to compare against? And now 3I ATS. Chemistry that doesn't fit. Trajectory that doesn't fit. Behavior that doesn't fit. 3 visitors, 3 very different profiles. What if they weren't random? What if Oumuamua was the scout? Fast, light, designed to map gravity wells and measure stellar environments. What if Borisov was the sampler? Collecting data, testing chemical pathways, evaluating atmospheric conditions. And what if 3I ATS is the delivery vehicle? The one carrying the payload? Scout, sample, seed. Not fact, not theory. Just a pattern. A pattern that would make sense if someone, something, was methodically surveying and seeding star systems across the galaxy.
You know what's going to happen, right? Tomorrow, someone's going to ask you what you watched last night. And you're going to pause. Because how do you explain this? You can't just say, a video about a comet. That sounds boring, dismissible. But you also can't say, evidence that aliens are seeding life throughout the galaxy, because that sounds crazy. So you'll probably land somewhere in the middle. There's this object from another star system, and it's heading for Jupiter in a really weird way. And they'll nod politely, maybe ask a follow-up question, maybe not. But here's what you won't tell them. You won't tell them about the feeling you had at 2 a.m. when you realized that Earth might not be the center of anything. You won't tell them how strangely calming it was to imagine the universe running processes we've only just started to notice. You won't tell them that for the first time in years, you felt small in a way that didn't hurt. Because some things don't translate into casual conversation. Some realizations are too quiet, too personal. They only make sense in the dark, with headphones on, when the world has gone silent and you're finally alone with your thoughts. Let me share something that doesn't make it into the press releases. I've spoken to 6 researchers working on 3i.atlas. Not for quotes, not for headlines, just conversations over coffee, late-night emails, Zoom calls where the camera's off and the guard comes down. And there's a pattern in what they say. None of them want to be the person who declares this thing artificial. Not because they're scared of being wrong, but because they're scared of being right. Dr. Marcus Liu told me something that stuck. If I stand up and say this is an engineered object, my career changes forever. I become the alien guy. Every paper I write gets filtered through that lens. Every grant gets scrutinized differently. He paused. But if I say nothing, and we find out later that I was looking at the first confirmed interstellar probe and stayed quiet, I'll never forgive myself. That's the position these people are in. Damned if they speak, haunted if they don't. Dr. Elena Vorontsova said it differently. I didn't get into science to make history. I got into it to understand comets. Now I'm staring at something that might rewrite astrobiology, and I can't even tell my family why I'm not sleeping. There's a weight in that, a human cost we don't see in the data. These aren't characters in a documentary. They're real people carrying impossible questions with no good answers. And they're doing it quietly, professionally, without the luxury of certainty.
Here's something I didn't mention earlier because it felt too heavy for the main narrative. But you're still here, so you can handle it. In 2005, when Cassini discovered water plumes erupting from Enceladus, NASA celebrated publicly. Press conferences, interviews, headlines about life-friendly environments in our own solar system. But privately, something else happened. A small group of scientists started asking uncomfortable questions. If Enceladus has liquid water, organic molecules, and energy, and if it's been like that for millions of years, and if we've already detected 3 interstellar visitors in 7 years of looking, what are the odds Enceladus is still empty? That question never made it into the press releases. Because once you ask it, you can't unask it. And it forces you to consider something profoundly unsettling. What if Saturn's moon, the one we've been studying, imaging, celebrating, already has something living in its ocean? Something that arrived long before we learned to look up. Something that's been growing, quietly, patiently, in the dark. And if that's true for Enceladus, what about Europa?
Let's do some math. Not complicated, just perspective. The Milky Way galaxy is roughly 13 billion years old. Human civilization, agriculture, cities, writing, is about 10,000 years old. That means the galaxy had 13 billion years to figure out how to spread life before we even learned to plant wheat. If just one civilization arose even 1 million years before us, and if they discovered a way to send seeds between stars, they would have had enough time to seed thousands of systems, maybe tens of thousands. And we would never know, because those seeds don't announce themselves, they don't broadcast, they don't build monuments. They just deliver and wait. Dr. James Corr ran a simulation once, not for publication, just curiosity. He modeled a single self-replicating probe spreading through the galaxy at 10% the speed of light. Within 10 million years, it could reach every star system in the Milky Way. 10 million years sounds like forever to us. But to the galaxy, it's a rounding error, a blink. And if that process started even once, just once, billions of years ago, the galaxy wouldn't be empty anymore. It would be full. Not with spaceships, not with signals, but with seeds, sleeping, waiting, hidden in ice and silence. We've been looking for radio signals for 60 years. Maybe we should have been looking at comets instead. Let's say, just for a moment, that everything we've discussed is true. 3I-ATLS is a seed carrier. Europa is the target. Life spreads through the galaxy by design. What changes for you? Not in a cosmic sense, in your actual life. You still have to go to work tomorrow, pay bills, make dinner, deal with traffic. The mundane machinery of existence doesn't stop just because the universe got more interesting. But here's what might shift. The next time you look at the night sky, you won't see emptiness. You'll see infrastructure. Not chaotic, not accidental, but purposeful. The stars won't just be distant suns. They'll be waypoints, tools, anchors in a delivery network older than memory. And the planets won't just be dead rocks. They'll be soil, potential, places where something might already be growing. That shift from cosmic loneliness to cosmic connectivity changes something deep inside. It means we're not alone in the way we always feared. We're not the first, not the only, not even the most interesting, but we're part of something. And for a species that spent its entire existence wondering if anyone else is out there, that answer, even an uncertain one, is profound. But
But it also means we have responsibilities we never signed up for. If Europa's ocean might already be seeded, then drilling through the ice isn't just exploration, it's archaeology. Or worse, disruption. Imagine if we drill down, release our probes, send back data, and accidentally contaminate something that's been growing undisturbed for 1,000,000 years. We'd be the equivalent of a toddler wandering into a centuries-old garden and pulling up every plant because they look interesting. Dr. Sarah Lynn said it plainly. Planetary protection used to be about protecting Earth from alien contamination. Now we have to consider protecting them from us. That's the ethical weight scientists are carrying. And it's not hypothetical anymore. Europa Clipper launches soon. The lander mission is in development. Within a decade, we'll have drills capable of penetrating that ice. And if we use them without understanding what might already be there, we could destroy the most important discovery in human history before we even realize it exists. That's the price of knowledge. Once you know something might be there, ignorance stops being an excuse. There's one question I haven't addressed yet, and I've avoided it deliberately because it's the hardest one. But you're thinking it, so let's say it out loud. If 3I/Atlas is a seed carrier, and if life spreads through the galaxy by design, where did the first seed come from? Because someone, somewhere, had to be first. Someone had to arise naturally, look up at the stars, and decide to spread what they had. Not for profit, not for conquest, just because they could. That question, who was first and why did they care, is the one that keeps me awake. Because it implies something almost religious. That somewhere, billions of years ago, a species arose that looked at the emptiness of space and felt responsibility. Not to dominate, not to colonize, but to share. To take the gift they'd been given, life, consciousness, awareness, and pass it along. That's not science fiction. That's mythology. The idea that intelligence, once achieved, feels an obligation to spread life rather than hoard it. I don't know if that's true, but I want it to be.
Here's what I've learned from spending months researching this story. Wonder isn't about having answers. It's about living comfortably with questions. Most of the things that fascinate us, consciousness, love, art, the universe, don't have clean explanations. And that's okay, because the questions themselves are the gift. The moment you stop wondering is the moment you stop being fully alive. 3I Atlas isn't just a comet, it's an invitation. An invitation to look up, to ask bigger questions, to sit with uncertainty and feel awe instead of anxiety. You don't need to believe it's artificial to appreciate what it represents. You just need to let it stretch your sense of what's possible. Because even if Atlas is completely natural, even if every strange thing about it has a mundane explanation, it's still an object from another star. It still crossed light years of emptiness to visit our corner of the galaxy. It still survived radiation, cold, and time that would obliterate anything we've ever built. And it's still here, right now, moving through our solar system while you sleep. That alone is worth your attention. So here's my promise to you. I won't hype this. I won't exaggerate. I won't turn uncertainty into clickbait. But I will stay with this story. When perihelion happens, I'll break down what we see. When Earth's closest approach arrives, I'll walk through the data. And when Atlas reaches Jupiter in March 2026, when we find out if something changes, if the mystery deepens or resolves, I'll be here. Not because I have answers, because I have the same questions you do. And I think those questions are worth asking together. You don't have to subscribe, you don't have to do anything. But if you care, if some part of you wants to know what happens next, come back. Because the universe is unfolding, and we get to watch. So let me leave you with this. Right now, as you listen to these words, Three-Eye Atlas is out there. Silent, cold, patient. Drifting through the dark at thousands of miles per hour, carrying whatever it carries, heading for whatever destination it was aimed at millions of years ago. It doesn't know you're watching. It doesn't care. But you're watching anyway. And that act, choosing to pay attention to something vast and strange, is what makes you human. Not intelligence, not technology, not dominance. Curiosity. The willingness to look up and wonder. So keep looking. Keep wondering. And when the night feels too heavy, when the questions feel too big, remember this. You don't have to understand the universe to be part of it. You just have to be here, breathing, alive, watching the stars. That's enough. It's always been enough.